Good morning, everyone. I'm Rahul Chowdhury, and welcome to our comprehensive course on operating systems concepts. Today, we're embarking on an advanced deep dive that will take us far beyond the basics into the fascinating world of kernel internals, performance optimizations, and real-world system challenges. This isn't just another theoretical OS course. We'll be exploring kernel internals, performance optimizations, and real-world scenarios that you'll encounter in production systems. My goal is to help you understand not just the what, but the why behind every implementation detail we discuss. Let me give you an overview of the advanced topics we'll be covering throughout this session. We'll start by diving deep into kernel architecture, exploring how virtualization works at the hardware level, and understanding the intricacies of the networking stack. These foundational concepts will prepare us for the more complex topics ahead. One of the most exciting aspects of this course will be our performance analysis section, where we'll examine real case studies from industry giants like Google and ByteDance. You'll see how these companies tackle performance challenges at massive scale. We'll also take a comprehensive deep dive into memory management, focusing particularly on page tables and virtual memory systems. This is where theory meets practical implementation in fascinating ways. Finally, we'll explore system debugging and failure analysis techniques, including kernel debugging methods that will be invaluable in your future systems work. Remember, throughout this entire course, our focus will be on understanding the why behind implementation details. It's not enough to know that something works. We need to understand why it works that way, what trade-offs were made, and how we can apply these principles to solve new problems. Are you ready to dive deep into the fascinating world of operating systems? Excellent. Now that we've established our foundation in operating systems concepts, let's dive into something that's absolutely crucial for understanding how your code actually becomes a running program: the compilation and linking process, and how it integrates with the operating system. Today, we're exploring compilers and linkers in their system context. This isn't just about turning source code into executables. We're looking at how this entire process works hand in hand with the operating system to create efficient, secure, and well-organized programs. Let's start with the compilation pipeline. We have four distinct phases: preprocessing, where macros and includes are expanded; compilation, where source code becomes assembly; assembly, where we get machine code; and finally linking, where everything comes together into an executable. Each phase has specific interactions with the operating system. Now, here are the key system integration concepts we need to master. These aren't just academic concepts. They're the foundation of how modern software actually runs on your machine. First, static versus dynamic linking. This directly impacts how the OS manages memory and loads your programs. Then we have memory layout with text, data, BSS, heap, and stack segments, each serving a specific purpose in how the OS organizes your running program. Position-independent code enables shared libraries, which is crucial for memory efficiency. And finally, the ELF format and symbol resolution, the mechanisms that make it all work together seamlessly. Understanding these concepts will give you deep insights into performance characteristics, security implications, and debugging strategies. You'll see why some programs start faster than others, how shared libraries save memory, and what happens under the hood when you run any program on a Unix-like system. Building on what we just covered about linkers and runtime loading, let's now dive deep into one of the most fundamental concepts in operating systems: the great divide between kernel and user mode. This divide isn't just an academic concept. It's the foundation that makes modern computing secure, stable, and efficient. Every program you run, every system call you make, crosses this boundary. Let's start with CPU protection rings. Modern processors implement multiple privilege levels, with ring 0 being the most privileged kernel space where the operating system runs with full hardware access. Ring 3 is where your application's live user space with restricted access. This separation prevents user programs from accidentally or maliciously crashing the entire system. It's like having different security clearance levels in a building. Now, how do user programs request kernel services? Through the system call interface. When your program needs to read a file or allocate memory, it uses instructions like int0 ZADI on older x86 systems or the more modern SYSCALL instruction. This triggers a carefully controlled transition from user mode to kernel mode through trap handling mechanisms. The processor switches contexts, validates the request, and executes the privileged operation on behalf of the user program. Memory isolation is another crucial aspect. Each process gets its own virtual memory space, and the hardware memory management unit enforces these boundaries. User programs simply cannot access kernel memory or other processes' memory directly. Virtual memory spaces ensure that even if a user program tries to access invalid memory addresses, it gets a segmentation fault rather than corrupting kernel data or crashing the system. However, this protection comes at a cost. Every mode switch involves context switching overhead, saving and restoring processor state, flushing caches, and updating memory mappings. This is why system call optimization is so critical in high-performance systems. Modern systems employ various optimization strategies like batching system calls, using memory-mapped I/O, and implementing user space threading libraries to minimize these expensive transitions. Understanding this trade-off between security and performance is essential for system designers. Now that we understand mode switching and system calls, let's dive into virtualization, one of the most transformative technologies in modern computing. Virtualization creates hardware abstraction layers that allow multiple operating systems to run on a single physical machine. This fundamentally changes how we think about resource allocation and system isolation. The key to virtualization lies in hypervisor architectures. There are two main types, each with distinct advantages and trade-offs. Type 1 hypervisors, also called bare metal hypervisors, run directly on the hardware. Think VMware XC or Microsoft Hyper-V. They have direct hardware access, which means better performance and lower latency. Type 2 hypervisors depend on a host operating system, like VirtualBox running on your Windows or Mac. They're easier to set up but introduce additional overhead through the host OS layer. Modern virtualization relies on several key technologies that make it efficient and secure. Hardware-assisted virtualization through Intel VTX and AMD V extensions provides native CPU support for virtual machines. Memory virtualization uses techniques like shadow page tables to manage guest OS memory efficiently. I/O virtualization and device pass-through allow virtual machines to access hardware devices directly, reducing performance overhead. Understanding these technologies is crucial because they directly impact system performance and resource utilization in virtualized environments. Building on our exploration of hardware virtualization, let's now dive into containerization, a fundamentally different approach to resource isolation that operates at the operating system level rather than the hardware level. Containerization represents OS-level virtualization, which means we're creating isolated environments within a single operating system kernel, rather than virtualizing entire hardware stacks like we saw with hypervisors. The foundation of containerization lies in Linux namespaces, a kernel feature that provides process isolation by creating separate views of system resources. Let's examine the key namespace types. PID namespaces isolate process trees. Network namespaces provide separate network stacks. Mount namespaces create isolated file system views. User namespaces map UIDs and GIDS, and IPC namespaces separate interprocess communication mechanisms. While namespaces provide isolation, control groups or C groups handle resource limiting and accounting. This is what prevents one container from consuming all system resources. C groups can limit CPU usage, restrict memory allocation, control I/O bandwidth, and manage device access, giving us fine-grained resource control that's essential for multi-tenant environments. The container runtime architecture forms a layered system. Docker Engine provides the user interface, Containered handles container lifecycle management, and Runk actually creates and runs the containers using kernel primitives. Security and performance are critical considerations in containerization. We use capabilities for fine-grained privilege control and seccomp for system call filtering, while achieving near-native performance compared to the overhead introduced by full virtualization. This OS-level approach gives us the isolation benefits of virtualization with significantly lower overhead, making containers ideal for microservices architectures and cloud-native applications. Next, we'll explore how major tech companies have optimized these fundamental kernel mechanisms. Now let's dive into a fascinating real-world case study that perfectly illustrates the concepts we've been exploring. We're going to examine how Google achieved remarkable performance improvements in their Linux TCP/IP stack optimization. This is truly impressive. Google managed to achieve a 40% performance improvement in their Linux networking stack. This isn't just theoretical optimization. This is production-level enhancement that directly impacts billions of users worldwide. Let's break down the key optimization techniques they employed. Each of these represents a different layer of the networking stack where strategic improvements were made. First, TCP/BBR congestion control. This is Google's own advanced algorithm that fundamentally changes how TCP adapts to network conditions. Unlike traditional algorithms that react to packet loss, BBR proactively estimates available bandwidth and minimizes latency. Next, receive packet steering. This technique optimizes CPU affinity and load balancing for network interrupts. By intelligently distributing packet processing across CPU cores, they eliminated bottlenecks that we discussed in our kernel versus user mode analysis. TCP fast open and multiplexing reduce connection establishment overhead. Remember our discussion about system call costs. These techniques minimize the expensive round trips typically required for connection setup. Finally, kernel bypass using DPDK. This is the ultimate optimization where packet processing happens directly in user space, completely avoiding the kernel overhead we've been studying. This represents the most aggressive approach to eliminating mode switching penalties. These optimizations demonstrate how understanding fundamental OS concepts, like we've covered with system calls, kernel boundaries, and CPU scheduling, enables engineers to identify and eliminate performance bottlenecks at scale. This is systems engineering at its finest. Building on our TCP/IP stack optimizations, let's now examine another fascinating real-world case study, ByteDance's approach to Linux reboot optimization for their massive TikTok infrastructure. When you're running a platform serving hundreds of millions of users globally, every second of downtime matters. ByteDance's infrastructure team faced a critical challenge: how to minimize the time it takes for their Linux servers to reboot and return to service. Their optimization journey began with a deep analysis of the entire boot process. They examined each stage: BIOS initialization, bootloader execution, and kernel startup, to identify bottlenecks and inefficiencies that could be eliminated. One of their most impactful innovations was reimagining service startup strategies. Instead of the traditional sequential service initialization, they implemented intelligent parallel startup mechanisms while carefully managing service dependencies to avoid conflicts. They also focused heavily on performance tuning through memory preloading and cache warming strategies. By intelligently preloading frequently accessed data and warming CPU caches during the boot process, they significantly reduced the time to reach full operational capacity. Since ByteDance operates massive data centers with standardized hardware configurations, they leveraged this consistency to implement hardware-specific optimizations that wouldn't be practical in heterogeneous environments. Finally, they established comprehensive monitoring and metrics collection to continuously measure reboot performance and identify new optimization opportunities. This data-driven approach ensures their improvements remain effective as their infrastructure evolves. These optimizations demonstrate how understanding the entire system stack from hardware to application layer enables breakthrough performance improvements at scale. Now that we've explored performance optimization case studies, let's dive into a critical aspect of distributed system reliability: timeout mechanisms. Understanding how timeouts work and fail is essential for building resilient systems at scale. Timeouts are your first line of defense against cascading failures in distributed systems. They prevent your application from waiting indefinitely when dependencies become unresponsive. Let's start with network timeouts. These operate at the connection level. They control how long your system waits for network operations, like establishing connections or receiving responses. Application timeouts work at a higher level, focusing on business logic constraints. These are often more generous than network timeouts, but equally important for user experience. Exponential backoff with jitter is a sophisticated retry strategy. The exponential component prevents overwhelming failing services, while jitter prevents the thundering herd problem where all clients retry simultaneously. Circuit breakers implement failure detection patterns that can save your entire system. They monitor failure rates and temporarily stop making requests to failing services, giving them time to recover. TCP timeouts operate at the kernel level and can be tuned through system parameters. Understanding these lower-level mechanisms helps you make informed decisions about application-level timeout values. Finally, cascade prevention is about system-wide resilience. One failing component shouldn't bring down your entire distributed system. Proper timeout configuration creates isolation boundaries that contain failures. Now let's examine a fascinating real-world case study that brings together everything we've learned about TCP/IP stack optimization and timeout mechanisms. This PostgreSQL Cisco router failure analysis shows exactly how cross-layer networking issues can manifest in production systems. This case study involves a critical database failure where PostgreSQL connections were mysteriously dropping, but the root cause wasn't in the database itself. It was in the network infrastructure, specifically how Cisco routers were handling TCP connections. The first area we need to understand is TCP connection state tracking. Routers don't just forward packets, they maintain stateful information about active connections, and this state tracking can become a bottleneck under high load conditions. On the application side, PostgreSQL's connection pooling mechanism was configured to maintain persistent connections, expecting TCP keep-alive messages to maintain these long-lived database sessions. But here's where the problem emerged. The Cisco router's internal buffers were experiencing overflow conditions during traffic spikes. When buffers overflow, the router starts dropping packets, including those crucial TCP keep-alive messages that PostgreSQL was depending on. Let's look at the key analysis areas that helped diagnose this complex issue. Notice how this required expertise across multiple layers of the network stack. The investigation focused on TCP keep-alive configuration, both on the PostgreSQL side and the router's handling of these packets. Router buffer management was critical, as undersized buffers were the smoking gun causing packet drops during peak traffic. The solution involved implementing comprehensive network monitoring strategies to detect buffer utilization before it became critical, and carefully tuning connection timeout values to be more resilient to temporary network hiccups. This case perfectly illustrates why understanding the entire stack from application to network hardware is essential for robust system design. Building on our network stack analysis, let's now dive deep into another fundamental OS component that's absolutely critical for modern computing. Today, we're exploring page tables, the foundation of virtual memory management. This is where the OS creates the illusion that each process has its own dedicated address space, even though they're all sharing the same physical memory. Modern systems use a multi-level page table hierarchy to efficiently manage virtual-to-physical address translation. This isn't just a simple lookup table. It's a sophisticated tree structure that balances memory usage with translation speed. In x86-64 systems, we typically see a four-level translation structure. The virtual address is cleverly partitioned into multiple page table indices, allowing us to traverse from the top-level page directory down to the actual page frame. The fundamental equation here shows how a virtual address breaks down into a virtual page number, plus an offset within that page. After translation, we get the physical address by combining the physical frame number with that same offset. Notice how the offset stays unchanged. That's the beauty of page-based memory management. Each page table entry isn't just a pointer. It's packed with crucial metadata including access permissions like read, write, and execute flags, plus validity bits and dirty bits for efficient memory management. The translation look-aside buffer is where the magic happens for performance. This hardware cache stores recent translations, turning what could be multiple memory accesses into a single fast lookup for frequently used pages. Huge pages are a brilliant optimization. Instead of 4 KB pages, we can use 2 MB or even 1 GB pages for large allocations. This dramatically reduces TLB pressure and improves performance for memory-intensive applications like databases. Finally, page fault handling implements demand paging. Pages are only loaded into physical memory when actually accessed. This allows the OS to run programs larger than available RAM and implements efficient copy-on-write semantics. Understanding these mechanisms is crucial for any systems programmer working with memory-intensive applications. Building on our foundational understanding of page tables, let's now explore the sophisticated optimization techniques that modern operating systems use to enhance virtual memory performance. These advanced optimizations are crucial for handling the demands of today's memory-intensive applications. First, let's examine inverted page tables with hash-based lookup. Unlike traditional page tables that map virtual addresses to physical addresses, inverted page tables work backwards. They're indexed by physical page frames and contain the virtual address information. This approach significantly reduces memory overhead, especially in systems with large virtual address spaces. Copy-on-write, or COW, is a brilliant optimization that delays actual memory copying until it's absolutely necessary. When a process forks, instead of immediately duplicating all memory pages, the kernel marks them as read-only and shares them between parent and child. Only when either process attempts to write does the kernel create a separate copy. This dramatically reduces memory usage and speeds up process creation. Memory mapping allows files to be treated as if they're part of the process's virtual address space. This enables multiple processes to share the same physical memory regions efficiently, which is particularly powerful for shared libraries and inter-process communication. The kernel can leverage the same page table entries across multiple processes, maximizing memory utilization. NUMA-aware page allocation becomes critical in multi-socket systems where memory access costs vary significantly based on physical proximity. The kernel must intelligently place pages close to the processors that will access them most frequently. Page compression techniques can also reclaim memory by compressing infrequently accessed pages, trading CPU cycles for memory space. These optimizations work together to create a highly efficient virtual memory system. Understanding these techniques helps us appreciate why modern operating systems can handle massive workloads while maintaining excellent performance characteristics. Now that we've explored page table optimizations, let's examine a critical aspect: security and protection mechanisms built into page table systems. Page table security has become increasingly important as we've seen sophisticated attacks like Spectre and Meltdown exploit hardware vulnerabilities. Let's start with hardware-based protection mechanisms. Hardware protection begins with execute never bits, also called XN or NX bits. These prevent code execution from data pages, stopping many buffer overflow attacks at the hardware level. Memory protection keys provide fine-grained access control, while Intel's Control Flow Enforcement Technology, or CET, helps prevent ROP and JOP attacks by maintaining shadow stacks. On the software side, we have several powerful protection techniques working in concert with page tables. Address space layout randomization makes it harder for attackers to predict memory locations. Stack canaries detect buffer overflows, while kernel page table isolation, or KPTI, separates user and kernel page tables to mitigate speculative execution attacks like Meltdown. These layered security mechanisms show how page tables aren't just about memory translation. They're a fundamental component of system security, protecting both user processes and the kernel itself from sophisticated attacks. Now that we've covered the security aspects of page tables, let's shift our focus to performance analysis. Understanding how to measure and optimize page table performance is crucial for system administrators and performance engineers. Page table performance analysis involves examining how efficiently our virtual memory system is working and identifying bottlenecks that could impact application performance. First, let's look at performance profiling tools. The Perf Toolkit is invaluable for analyzing TLB misses, page faults, and memory access patterns. You can use commands like perfstat to measure TLB miss rates and perfrecord to capture detailed memory access traces. System metrics provide another layer of insight. The /proc/meminfo file shows us overall memory usage, while /proc/vmstat reveals detailed virtual memory statistics including page fault rates, swap activity, and memory allocation patterns. Configuration testing is essential for optimization. By benchmarking different page sizes, from 4 KB standard pages to 2 MB huge pages, we can determine the optimal configuration for specific workloads. Memory access pattern analysis helps us understand which applications benefit most from larger page sizes. Finally, production debugging skills are critical when dealing with memory-related performance issues. This includes identifying memory bottlenecks, analyzing page table overhead, and implementing targeted optimizations based on real-world usage patterns. These analysis techniques form the foundation for making informed decisions about virtual memory configuration and optimization in production systems. In our next section, we'll put all these page table concepts together for comprehensive mastery. As we reach the culmination of our comprehensive journey through advanced operating systems concepts, let's synthesize everything we've learned and explore where this field is heading. Throughout this course, we've seen how integration patterns tie everything together. The compilation process we explored in the early pages works hand in hand with virtualization layers, and both depend heavily on the memory management techniques we just covered. Understanding these interconnections is what separates good system architects from great ones. Looking ahead, emerging technologies like quantum computing are already challenging our traditional OS paradigms. The principles we've studied, from kernel user mode boundaries to virtual memory management, will need to evolve to support quantum computational models and their unique requirements. Most importantly, you've developed the performance engineering mindset that's essential for systems architects. Remember the case studies we analyzed, from Google's TCP/IP optimizations to ByteDance's reboot strategies. They all demonstrated this systematic approach to identifying bottlenecks and implementing targeted solutions. Your key takeaways from this course should include a solid foundation in production system design, an understanding of how to approach continuous learning in this rapidly evolving field, and the confidence to tackle complex system challenges using the frameworks we've explored together. Remember, mastering these integration patterns enables you to design more effective, scalable, and robust systems. The journey doesn't end here. Keep experimenting, keep questioning, and keep pushing the boundaries of what's possible in systems engineering. Thank you for an engaging and productive session, everyone.